So I agree, C should not even be a triangle because 2 plus 10 is not greater than 12. So this is not even a triangle. So we probably should check to make sure it's a triangle before we can even check whether it's right, obtuse, or acute. Now, these are kind of the notes that you are supposed to have read through and looked at your homework for to decide whether or not, what kind of a triangle it was. So once you've checked to make sure it's a triangle to begin with, then we can plug these numbers in. What do A, B, and C represent? How do I know which one's A, which one's B, which one's C? Say it louder. Is what? Perfect. C is the largest side and A and B are the smallest sides. Yeah, that's that right. Perfect. So in this case, 5 is just going to be the largest side. So you would just check 4 squared plus 5 squared. Is that greater than, less than? What is that? So what is 4 squared plus 5 squared? You have calculators, so you can go ahead and do it now. What's 16 plus 25? 41. Is 41 larger or smaller than 25? Since the sum of the two sides is the square, the sum of the squares of the two smaller sides is larger, that would be this case here, where it's going to be an acute. The sum of the two smaller sides is bigger. So that would be an acute. So I agree. How about letter B? Do you agree that that's also acute? Let's check it, okay? Let's check it up here. 2 squared plus 10 squared, how does that relate to 11 squared? Well, the two smaller, when I add them together, I get 104, and that's going to be that was weird. That's going to be less than 121. So since the largest side squared alone, the bigger one is by itself larger, that's actually going to make this one a what kind of a triangle? An obtuse triangle, okay? So we've already checked C is not even a triangle to begin with. How about D? Do we agree with D? Yes. Okay, 9, 40, and 41. If those three things make a right triangle, there's a special name for those three sides together as a group. Do you guys know what it is? It's called a Pythagorean triple. Exactly, Brittany. Okay, so let's just check it. If 9 squared plus 40 squared equals 41 squared, then 9, 40, and 41 are considered a Pythagorean triple. Let's see if it works. I'm just going to borrow Jason's calculator real quick. So I have 9 squared plus 40 squared, and I get 1,681 on the left-hand side. And then when I do 41 squared, I also get 1,681. So I agree, it is a right triangle. And then the last one, they're out of order. Would you agree? So we have to be real careful here, and we have to put the largest by itself, and we have to compare it to the square of the sum of the squares of the two smallest. 10 squared plus 17 squared. With the calculator, this should be pretty quick. 389. And then we have 26 squared. And I got 676, which means that it's an obtuse triangle, so I agree with that one. Okay? This is called the Pythagorean converse, by the way. The converse of the Pythagorean theorem. The Pythagorean theorem says that if the sum of the squares of the two smallest equals the square of the largest, a squared plus b squared equals c squared, then it's a right triangle. But we can also look at the other two situations to decide whether or not what kind of a triangle it's going to be. Here are the answers to your homework, so go ahead and check those for me. Several people said they got confused towards the end, so I'd be glad to go over one of those if you want. So just check your homework real quick. All right, so on page 496, we're looking at problem 23 first. So let me go ahead and just kind of draw the picture. Let me read the problem because it's a word problem. It says, a walkway forms one diagonal of a square playground. So let's go ahead and make sure we start by drawing a square. And then we're going to draw a diagonal, okay? And it says here, the walkway is 24 meters long. To the nearest meter, how long is a side of the playground? Well, since it's a square, don't you agree that they both have to be the same? So if I call them, one side is x, doesn't the other one have to be x also? If it's a square, don't I also know we have a right triangle? So I'm really just looking at this scenario here. Okay, just this right triangle. And actually today, after we learn about what we call special right triangles, you'll be able to figure out that this is 24 divided by the square root of 2. But you don't know that part yet. So let's just use what we do know, the Pythagorean theorem. I know that x squared plus x squared is equal to 24 squared. Do we agree with that sentiment? Yes? No? I know y'all had like a million days off, but you awake? Right? So what do I do here? What's x squared plus x squared? 2x squared. There are 2 of them. And then what's 24 squared? I don't know. Off the top of my head. Do you guys know? Numbers are getting kind of big. 576? Okay. Now, before I can take the square root of both sides, what do I have to get rid of first? And how do I do that? Divide by 2. So what's 576 divided by 2? So at this point, my squared term is by itself. So I'm just going to take the square root of both sides. I would like it if we could go ahead and leave my answer in radical form. So let's make a factor tree. 288. Give me some numbers that go into it. 2 and 144? It doesn't really matter which ones you start with, believe it or not, because you'll end up with the same answer at the end. Okay? I would probably have picked that, probably would have picked 9 or a larger number to begin with, because that would simplify quicker, to be honest with you. But either way, it should work. Do you have a question? Well, actually, you're exactly right, but I probably would have done what India did, to be honest with you. But you're exactly right. This actually becomes the pair right away, and so it's just 12 radical 2. Yes.
So, when it comes down to this, when I multiply,
you do. Yes, you do. So 2 times 2 times 3. Yes, you should multiply. So it's 4 times 3, which is 12.
Okay.
Yep. And then you got the same answer, right? So it doesn't matter which 2 numbers you start with in your factor tree. Good. Doing okay? Hope so. All right. Let's go ahead and look at the next one, 33. Okay, so in question 33, we have a think about a plan. I've got an embroidery square inside of a circle. Well, the embroidery hoop, by the way, for anybody whose mothers do embroidery, there's a hoop that you have to stretch fabric across. And it's a square, which means that we have x and x. Okay. It says, what is the diameter of the circle represent in the square? So I'm going to draw the diameter. Remember, a diameter in a circle goes from one point through the other that passes through the center. The diameter of the circle is what of the square? Begins with a D. The diagonal, yeah. The diagonal of the square is the same thing as the diameter of the circle. Good. The next question says, what do you know about the sides of a square? What's true about the sides of a square always? They're all congruent. Okay. Next question. How do the side lengths of the square relate to the length of the diameter? Well, don't I know that if we're going to draw one of the right triangles, isn't x squared plus x squared equal to the diameter squared? That's all you had to say. That's all I was looking for. And there's actually a more specific. This is actually, we're going to learn this today. This is actually the square root of 2 times the side. We'll learn that eventually. Okay, and then 35. So let's look at that one. All right, 35 says, we have a coordinate proof. So let me kind of start it for us. Just redrawing the picture that we have here. This is a very typical SOL question, by the way. We like to put these x1, y1, x2, y2 letters. So we're told that this is true. Okay. It says, write an algebraic expression to complete each of the following. The length of PR. So it says PR is equal to what? Well, how do I take this PR and plug in what I know? Can't I just use the distance formula here? Isn't it just this squared minus this? Remember the square root? Remember the formula for distance? So isn't it the sum of the differences of the x's and the sum of the differences of the y's? So if we say x1 minus x2, y1 minus y1. What do you notice about y1 minus y1? Isn't that just 0? So isn't it just this? Right? Would you agree with that? Well, the square and the square root undo each other. Do you agree with that? The only problem I have with leaving my answer this way is that doesn't it depend on the order in which I subtract? Couldn't I have a negative number if I did x1 minus x2? If this was a smaller number? Do you see what I'm saying? So to make up for that, the order in which you subtract, you could have a negative answer or a positive answer. And since it's length, what do we always want? So to make up for that, we're just going to say it's that. Absolute value means it's always positive. We don't have to worry about it that way. Okay? All right, and then the next question says, part B, by the Pythagorean theorem, it says rewrite this statement by putting what you know. So we know that by the Pythagorean theorem, it says that PQ squared equals PR squared plus QR squared. Well, what did we just find? Didn't we just find PR? So let's just plug that in. PR squared would just be this squared, okay? So x1 minus x2 squared. And then we'd have to plug in PQ. Well, we'd substitute that information in as well by plugging in the length here. So we're going to say x1 minus, and it's the square root of all this, x2, just subtracting the x's, and then we'll subtract the y's. And over here we'll do QR. QR, you'll find, will be the very similar. Can't you just count up? So when you subtract the x's, what do you get? You get 0. So this one is just going to be y2 minus y1, just like this one was, squared. That's all they just wanted you to plug and chug. Okay, don't worry too much about that. Just wanted you to plug and chug. And then it just says take the square root of each side, or take the square of each side to simplify. We don't have to go that far. Okay, just plugging it in. Basically, the important part of what I want you to come up with is, can I get to this point? Can you see that that's why absolute value is important in this case? Do you understand why it is? If you don't, tell me so I can help you. Why is someone rephrase it? Why is it important to put absolute value marks there? Marvin, explain it. Right. So if I go ahead and put absolute values, isn't the absolute value of -6 positive 6? So it means all that means is you're always going to get a positive answer. The order in which you subtract them doesn't matter. That's all. That's why they're there. Okay? All right. What I'd like us to do is really quickly look at a couple of different Pythagorean theorem problems, make sure we fully understand what they're saying. Go ahead and put these into your notes, and then we're going to move on from there and look at the special rights. But for now, 2 examples. We're going to call this the converse of the Pythagorean theorem. We're going to do 2 problems in our notes for the converse, and then we're going to do special rights. This is the right triangle unit. We're actually starting a new section in your binder. So in the binder for this semester, you should already have a section on similar triangles, right? Similar triangles, correct? Because everything before similar you could have taken out. You can leave it if you want, but don't lose it because we'll bring it back at the end of the year. So we should have similar, and now we're going to do right. Okay, right triangles is the next section. So we're going to take just a couple of examples on the converse of the Pythagorean theorem. And then we're going to also do special right triangles today. Okay. And today is the 19th of February. And let's look. So these next two examples should just be in the converse of the Pythagorean theorem. So make sure you put this in your notes with that title, okay? So we're going to need to draw a picture and label according to the problem. So write the problem down. I do want you to write the words down. I think it's important to know what the words are saying and what part goes to what. One of the questions on your test that you took where it talked about the altitude of the right triangle was adjacent to the smaller part of the blah, 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 and you had to draw the picture, caused some problems for a lot of us. So I think we need to practice being able to read a word problem and identifying what goes where in the problem. So as you're writing the problem down, I want you to think about a ladder and how it's going to be propped up against the wall. What part of the right triangle is the ladder? Let's use the vocabulary. It's going to be the hypotenuse. What are the other two sides in a right triangle called? If we know what the hypotenuse is, what are the other two sides called? Legs. Okay, good. And sometimes the legs are congruent. Sometimes one's longer than the other. We're not sure. But we always know the hypotenuse is the longest side. And it's across from the right angle. So we know that part. So we can kind of imagine that this is our ladder, if you want to think about it that way. Okay? So the base of the ladder is 6 feet from the wall, and the ladder itself is 25 feet long. I'm just going to uncomplicate my picture. Where does 25 go? It's the hypotenuse. Where does 6 go? On the bottom leg, okay? So we're going to call that 6. And it says, how far up the wall will the ladder reach? So what should I label that as? X, perfect. If we know something about 2 of the 3 sides of a right triangle, you can always find the third side. Eventually in this unit, we're going to only know one part of the triangle, one side, but we might know an angle. Okay? If we know a side and an angle, then we can also find some other information. Okay? We can also use this, and knowing all 3 sides of the triangle, eventually we're going to learn how to find the angles of the triangle. Okay? We've never done that before. Yes, the sine, cosine, tangent. We're going to eventually get there, okay? But right now, we don't care about the angles. All we care about is the length of the sides. And so we know what we can use. It's Pythagorean theorem. So tell me what I would write. Good. X squared plus 6 squared is equal to 25 squared. I agree. And at this point, we probably should go ahead and plug the 6 squared and the 25 squared in and get an answer. So what is 6 squared? Okay, and then 25 squared? Double check. It's not 225, but it's 625. Just off by 2/3. All right, and then to solve for x, we can't take the square root yet. What do we need to do? Subtract to 36. And what is 625 minus 36? 589. Is that a perfect square? Try. Is the square root, because at this point we take the square root of both sides, right? No. It's not a perfect square, okay? So you really need to think about how I want your answer. Do I want, it will say round to the nearest tenth or something like that if it wants a decimal. Does it say that here? No. So unless it tells you to round to a certain place, we should always assume to leave our answer in radical form. for practice with radicals, okay? So let's go ahead and just reduce our radical here. Give me some numbers that go into 589. $19 and what? 19 and 31? You sure about that? Are those both prime numbers? They are. So can you reduce that radical? No. So you would leave it as a square root of 589 because you can't reduce it any further. But if we're trying to, let's say I tell you to round to the nearest tenth. The nearest tenth of a foot. Actually, let's do it this. Let's round to the nearest inch. How would I do that? So what is this approximately as a decimal? All right, so let's just say 24.27. Okay, let's just be a little bit more exact. Okay, now I'm going to put this. I'm just going to put it exactly in my calculator because it's important to be. Don't round. You don't want to round at this point. So the square root of 589. You got this. I agree. So we know, for example, it's 24 feet. Would you agree with that? So we know it's 24 feet. How many inches can I say? Well, how do I figure out how many inches that is? I'm going to subtract 24 because I don't really care about the 24 at this point, do I? I just care about the decimal portion. That is 0.27 feet. How do I convert that to inches? I want to multiply. How many inches are in a foot? So if I just multiply this by 12, that will give me 3 inches. Okay? Well, we don't want it, so to the nearest inch would be 3 inches. Okay? So about 24 feet, 3 inches up. Okay? How do you guys feel about that? Okay? So obviously, if we have a word problem, I want you to draw me a picture, always, and label what you know, and then just show the work that goes along with it. All right. Brittany said earlier that something was a Pythagorean triple. Just remind us, what is a Pythagorean triple? What does it have to do to be a Pythagorean triple? Go ahead. Say what, baby? Non-zero? Yeah, they're definitely going to be lengths, I agree, but what makes them specifically a Pythagorean triple? I know Marvin knows. Somebody else? Okay, so I would have to make a right triangle, which means it's going to do what? You're right? Keep going. If it's going to make a right triangle, what's it going to have to satisfy? A squared plus b squared is going to do what? Equal c squared. So I want you to check all of these. Is this true for all, some, or none of these three? Are they Pythagorean triples? You can quickly check it on your calculator if you want. Okay? You can just simply say 5 squared plus 12 squared, and then you can do 13 squared. So you, oops, I didn't do that right, did I? 5 squared plus 12 squared, and then 13 squared. And you can see right away, is A a Pythagorean triple? Yeah, because it satisfies Pythagorean theorem. How about B? Check B and C. I want you to do it for me. You chest one. Obtuse? Okay, I agree that this one is. That's a Pythagorean triple. And then if we did 7 squared plus 9 squared, oh goodness, that wasn't what I meant. 7 squared plus 9 squared. And then it was 16 squared. I definitely got that this to be true. Would you agree? With the one by itself, the longest side squared was longest, so that would be an obtuse triangle. So not a Pythagorean triple. There are some very common Pythagorean triples. These are 2 of them, but you may recognize 3, 4, 5 as a Pythagorean triple. There's obviously multiples of all of these would also be Pythagorean triples. So if I multiplied all of these by 2, 6, 8, 10 would be a Pythagorean triple. If I multiplied the originals by 3, I would have 9, 12, and 15 as a Pythagorean triple, right? So they all work that way, okay? They're very common. So does it satisfy the Pythagorean theorem? Okay, good enough. All right. Now, we have special right triangles. You want to put a new heading into your notes here. This is going to be new to us. And we're going to talk now about a kind of right triangle that has it's a special case of right triangles because the angle measurements go 45, 45, 90. Okay? So in other words, it would be drawn like this. The angles would be 45 degrees and 45 degrees. I do, yes. Okay? You're going to do two cases, case 1 and case 2. Can you classify this kind of triangle? We obviously know it's a right triangle, but what other name might be associated with it? Isosceles, right. Because if I have two congruent angles, if we kind of treated that as the base, wouldn't I have two congruent angles? So it's an isosceles triangle. In other words, these two sides are congruent. So sometimes we call the case 45, 45, 90 the isosceles right triangle case. Okay, they means the same thing. So it's also the isosceles right triangle. Now, every single isosceles right triangle has the same ratio of the sides. So we just finished similar triangles. And so every single 45, 45, 90 triangle out there in the world will have the same ratio of the sides. And that kind of makes sense. If I had a little 45, 45, 90 and a big one, wouldn't they be similar by angle, angle? So we know that they're going to be similar triangles, but what is that ratio? The ratio is 1 to 1 to the square root of 2. Okay? Now that's the ratio, which means it's reduced as much as possible. We could multiply all of those by a factor of 2, 3, 4, 5, whatever, and get a different ratio for the actual triangle. But this is our reduced form. Another way to think about it is, if I know one of the sides, one of the legs, don't I automatically know the other one? If I know one of the legs, can I find the hypotenuse? Sure. I know that it's 1 times the square root of 2. Sometimes you put a 1 out here so you can recognize that it's the leg times the square root of 2. Here's an example. Don't write this down, but just watch. If, for example, I knew that this leg was 6, what would this leg have to be? 6. What would this be? 6 radical 2. Okay? So if I know one of the sides, or one of the legs, I can find all the others. No problem. So we always like to say 1, 1 square root of 2 as kind of the reduced ratio. Okay? So let's look at a couple of examples with this. Okay? And you can choose to write these down or choose not to. If you're going to write any of them down, write example 2, because it's the harder of the two. Okay? Go ahead and look at the first one. Based on what we just did, you should be able to answer what x and y are fairly quickly. Without doing any thinking, Eliodoro, which one can I answer, x or y, really quick? I know y, and what is it? Perfect. I know that y has to be 3, because it's an isosceles right triangle. They're marked congruent, for goodness sakes. So I know that the legs are both 3. Based on what I just told you, the length of the hypotenuse is going to be what? Radical 2 times 3. We usually write the number first, so it's just going to be 3 times radical 2. Agree. Not hard yet. What about example 2? Why is example 2 a lot harder than example 1? Because I gave you the hypotenuse this time. Now, if the hypotenuse said 6 square roots of 2, how would I find the legs? Wouldn't they just be 6? That's a no-brainer, isn't it? How did I do that? How did I go from the hypotenuse back to the sides? Backwards, I did what? If I went from the sides to the hypotenuse, I multiplied by the square root of 2. Down here, how did I go from here to here? I took 6 radical 2, and I did what to get the 6? I divided by the square root of 2, right? So if I have the leg and I want the hypotenuse, I'm multiplying. If I have the hypotenuse and I want the leg, I'm dividing. Get a question, Marvin? Let me finish. I'm not done. Okay? So because it's a 6 and not 6 radical 2, it becomes a little bit more difficult. So I know that x and y are the same. Would you agree with that part? I know they're equal. Yes, no? Okay with that part. But how do I get what the answer is? Well, what did I tell you? If you have the hypotenuse and you're working backwards to the sides, I take the hypotenuse and I do what with it? Divide by the square root of 2. Okay? 6 divided by the square root of 2. Now, normally I would say perfect, you're done, that's right. But in math land, they don't like to have radicals in the denominator. They want us to what we call rationalize our denominator. So it's a little side work. That is the answer. If I type 6 divided by the square root of 2 on my calculator, I would get approximately what the answer is as a decimal. Oh goodness, I'm typing in the wrong number. 6 divided by square root of 2. There we go. Okay? 4.24. It's approximately. Good enough. But if I have 6 divided by the square root of 2, and I want you to leave your answer in reduced radical form, this is not, because there is a radical in the denominator. To rationalize it, you're going to multiply by 1. If I multiply by 1, do I change anything? Like 7 times 1, 3 times 1, it stays the same, doesn't it? And isn't anything over itself just 1? So isn't this just like multiplying by 1? Why did I choose that ugly thing? Well, that's because that's what the denominator says. Okay? So, Maddie, you should be writing this down. Okay? When I multiply the top, it's just 6 radical 2. What is the square root of 2 times the square root of 2? The square root of 4, which is just 2. So that's the point, is we wanted the radical to go away. And it does. This number here is what you're choosing to multiply because it's the denominator. And when you multiply fractions, you multiply straight across. What else do you notice about these two things? Now, it's under the square root because you can't simplify that, but outside of it, isn't 6 divided by 2 just 3? So my answer here becomes 3 square roots of 2. Now, if I type into my calculator 3 square roots of 2, I get the same thing. So I know I did it right. Josh. The square root of 6 is wrong. Where'd you get that from? I'm confused. I'm done? Okay. You answered your own question? Perfect. I'm not even sure what it was. That's okay. So 4.24 is approximately the answer. Yeah, because they're both the same. But I want you to leave your answer in reduced radical form, so this would be the most correct and accurate answer. Yes, Marvin?
What about if you have in the bottom a value of that only?
That's called a conjugate, and that's something totally different. It's above the level of this class. That's would be algebra 2. Okay? But yes, you would multiply by the number, the sign in the middle would be different. Okay? Yes?
Wait, so they're not marked the same, but is it always the same no matter what? Or?
If it's a 45-45, yes. Okay? Yes. So isosceles right in every case in that way. So there's two possibilities with a 45-45-90. You either know one of the legs, and if you know the leg, isn't it pretty easy to find? That's the easy case, right? Or you can know the hypotenuse and have to work backwards to the legs. Remember, when you work backwards, you just divide. That's the only difference. Okay? Okay so far? All right. Let's look at an example. And this should look very familiar. You don't have to write it down because you probably already did. Just read it. Tell me why it looks familiar. Where did you do it? Homework. A similar one, not exactly this one, but a similar one. What's different about this one and the one that we did for homework? I don't know what the sides are. And what am I given instead? The perimeter. If I'm given the perimeter, how do I find the sides? Divide by 4. What is the side? 6. Good. So if each of these sides is 6, and I'm just looking at this triangle here, isn't that an isosceles, right? So how do I find the length of the diagonal? It's just 6 radical 2, because it's radical 2 times the leg. Quick and easy. You could do the Pythagorean theorem, which is what you did for homework, right? But that's quick and easy. Yes?
So if it's a question like that, you could always just put radical, so you don't have to do it.
Yeah. And honestly, on the SOL, they rely a lot on special rights. You'll see those 30, 60, 90s, our next case, and this 45, 45 comes up a lot. So it's really an important thing. I hate to say the word memorize, but you got to memorize it. Okay? I hate to say that, but you do. You just need to know them. But yes, 6 radical 2 is perfectly fine with me. All right. The last case that we're going to do today, okay? 30, 60, 90s. Notice that this one looks a little different. Does it look isosceles to you? No, does not look isosceles. Okay? You're definitely going to have a short leg, and you're going to have a long leg. And we know, because we know something about geometry, that if these are my angles, 30 degrees, 60 degrees, and 90 degrees, well, we know the 90, don't we? Which one is the 30? Which one does it have to be if this is drawn to scale, Deshay? Yeah, because it's across from the smallest side, right? Smallest angle across from the smallest side. I agree. Good. Now, I highlighted the short side for a reason. If you have a highlighter or a color or something, make it a lot darker of some kind somehow. Because, and you feel free to borrow one of the highlighters back in the back if you need to. But I highlighted it for a reason, okay? Everything in a 30, 60, 90 triangle revolves around the short side, okay? And remember how when we talked about the 45, 45, 90 was 1, 1, square root of 2? We're going to make the short side in the ratio that we're going to create a 1. The hypotenuse is always twice as long as the short side. So in our in our sample case, if the short side is 1, what's the length of the hypotenuse? 2. Perfect. It's always twice as long. And then the long side, the long leg, is always the square root of 3 times the short side. Now, we don't normally have to put the 1 there, but I'm just putting it there to remind us that it's the long leg times the short leg. Okay? So that's your base case. That's your base ratio of the sides. What's your question? The square root of 3 times the short side. Yep. So, for example, don't write this part down, but if this short side was a 4, what's the length of the hypotenuse? 8. If the short side is 4, what's the length of the long leg? 4 square root of 3. Okay? Everything is in relation to that short side. So you always want to find the short side first. And I can probably tell you that that sometimes happens and sometimes doesn't. But when you have the short side, we got it. So we're going to look at 2 cases. Okay? Yes. This is just the base ratio. How do you get it if you're not given it? We're going to look at that right now. Okay? So both of these examples are good ones to put in your notes. Okay? Both of them. Because in my mind, the 30, 60, 90 triangles are the more difficult of the 2. Because you've got the hypotenuse is twice as long, and then you've got one of the legs is the square root of 3 times as long. So let's look at both of these examples. Okay? But let's just do one at a time. So I'm going to cover up the bottom one. Do I have the short side? No. Can I find it? Pretty quickly. Divide by 2. Great job, Ingrid. So which one is that, X or Y? X. So I know that X is going to be 4. Perfect. Because the hypotenuse is twice as long. I divided by 2. I'm working backwards, so I'm doing some division. How do I get the long leg? This is the short side times square root of 3. Perfect. Done. That's it. That's how you want. I want you to leave your answer in radical form. Absolutely. The only thing you have to be careful of is if you have a radical in your denominator, like we did last time. And we're going to do another one here in a minute like that. We okay so far? As you can probably imagine, this last example is a little bit harder. Okay? So the second example is a little bit harder. I want you to look at it, and let's decide why it's a little bit more difficult than the others. We should double check, by the way, that we do have a 30, 60, 90 triangle. Do we? Okay, so it is one of our special cases. Do I have the short side? No, but I want it really badly. So we always want that short side, right? Well, what side do I have? The long leg. Well, since I'm going to go backwards from the long leg to the short side, I have to do some dividing. What am I going to divide by? Perfect. I'm dividing by the square root of 3. But what's the problem with leaving my answer this way? The radical in the denominator freaks us out in math land. Can't do that. So I'm going to purposely choose to multiply by a number that will be equal to 1, but I'm going to choose the square root of 3 over the square root of 3. Because I know that when I multiply the fractions straight across, the square root of 3 times the square root of 3 is the square root of 9, which is just 3. The radical goes away, which is what I wanted. And then what's in my numerator? 5 square roots of 3. And you have to leave, as ugly as it is, you leave your answer like that. You're jumping ahead, Indian. I love that. You're looking. So now we're trying to find, and I didn't label it X and Y, but now we want to find the hypotenuse. And what was the hypotenuse relationship to the short side? Times 2, twice as long. So how do I take 5 radical 3 over 3 and multiply it by 2? Well, when you multiply a fraction by a non-fraction, you can put it over 1. You know my denominator will still be 3. How do I multiply what's in the numerator? Does the 2 get multiplied by the 5, the square root of 3, or both? Just the 5. So the answer becomes 10 square roots of 3 over 3. So special right triangles do a lot with geometry, but they also do a lot with algebra. Okay? Being able to remember how to multiply fractions, do you remember how to deal with radicals, divide by radicals, get rid of the radicals in the denominator, etc. So I have put together some problems, and obviously there's no way you're going to be able to do all of them today, but they'll be due next class. And it's double-sided, and it will be turned in for a grade, okay? Not just a homework grade, but a grade. And it's on special right triangles, okay? And there are a total of 30 of them. Some will be quick, some will not. But I want to remind you that your answer, you may not have radicals in the denominator. I believe, I've got to double check, but I believe each of these have an X and a Y. So just double check, look through it for me real quick and just double check that that does happen. But I want you to go ahead and start working on it now, because this is just straight up. Do we remember what our two cases are? Is it a 30-60-90? Is it a 45-45-90? So you want to decide, because these are all mixed together. Okay? You do have some fractions, like number 11. If you look at 11, we've got fractional and radicals there. So you'll have to be real careful there. But I believe all of the angles are labeled here. I think so. Okay. So again, go ahead and write your answers right on here. This will be due next class, because you only have, what, 15 minutes or so? So you won't have enough time now. But you just need to make sure you have your two cases. Leave those cases in front of you so you know, is it 1-1 radical 2 or is it 1-2 radical 3? So for homework, you need to finish this, and it will be graded for accuracy next class, okay? Not just a homework grade. I'm sorry? You're going to finish it for homework, sure. But it's not a homework grade, it's a grade, but you're still going to take it home and do it.
Okay.
You're not going to get an additional homework assignment. This, is that good? Okay, okay. So I'm sorry, I'm not trying to be unclear. Okay.